Okay, so picture this. What if you could build a machine that solves problems in like minutes? Problems that would take our best supercomputers billions of years to even scratch the surface of. Well, that's not sci-fi, folks. That's the wild promise of quantum computing. And in this explainer, we're going to dive into the incredible origin story of this tech, how it went from a crazy idea to something that's literally changing our world. So, yeah, let's get right into it. So, let's really unpack that central promise for a second. I mean, this isn't just about making our computers a little bit faster, right? No way. We are talking about a complete, total paradigm shift. It's a leap so huge that it could completely rewrite our definition of what's even possible to solve. And honestly, this single idea, this is what's been driving the entire field for decades.
So, you're probably asking, how on earth is that even possible? Well, the answer comes down to one fundamental, game-changing difference. You see, every computer you've ever used, from your phone to the biggest supercomputers, runs on bits. And a bit is pretty simple, right? It's either a 0 or a 1, on or off. But quantum computers, they use something called a qubit. And this is where it gets wild. A qubit can be a 0, it can be a 1, or, and this is the part that will totally blow your mind, it can be both at the exact same time. Yeah, that property is called superposition, and it is the absolute secret sauce that gives these machines their unbelievable power. Okay, but an idea this revolutionary, it doesn't just pop up out of thin air, right? To really get where we're headed, we've got to rewind. We need to go all the way back to the very beginning, to the handful of brilliant minds who first dared to ask a pretty crazy question. What if we could actually compute using the fundamental laws of the universe itself? And it all started, really, in the world of pure theory. The first seed was planted back in 1980 by the one and only Richard Feynman. He had this simple yet totally profound insight. He said, look, nature plays by quantum rules. So if we ever want to truly simulate nature, we're going to need a quantum computer. A few years later, in '85, David Deutsch built on that and laid down more of the theoretical foundation. But the real earthquake, the moment everything changed, was in 1994. That's when Peter Shor came along and basically discovered the field's killer app. That one problem a quantum computer could absolutely crush, that a classical one, well, it just couldn't solve. Period. And this quote really hits the nail on the head as to why Shor's discovery was such a massive deal. I mean, think about it. Almost all of the digital encryption that protects our entire world, we're talking everything from your bank account to top secret government data. It's all based on one simple fact. It is ridiculously hard for regular computers to factor huge numbers. Well, Shor came along and proved that for a quantum computer, it's not hard at all. In fact, it's easy. And just like that, poof, quantum computing went from being this interesting academic thought experiment to a genuine matter of global security. The race was on. All right, so the theory is solid, the motivation is definitely there, but then comes the billion-dollar question. How do you actually build one of these things? This is the point where the story shifts, right? It moves off the blackboard and into the lab, where the really, really hard engineering problems were just getting started. And pretty quickly, two main approaches, two different camps really, started to form. In one corner, you've got superconducting qubits. These are basically tiny electrical circuits that have to be cooled down to temperatures colder than the vacuum of deep space. They're super fast, but man, are they delicate. Then, in the other corner, you have ion traps. Here, scientists are literally levitating individual atoms with lasers. These guys are way more stable, but they're also a lot slower. But you know what? The core challenge was exactly the same for both. How in the world do you build a machine that's both stable and scalable out of these incredibly fragile parts? And all that work brings us pretty much to where we are right now, which is what experts call the NISQ era. It stands for Noisy Intermediate Scale Quantum. And I actually love this term because it's just so honest. Noisy basically means our quantum processors are powerful, for sure, but they're still imperfect. They're prone to errors, they're easily knocked off balance. But here's the key thing to remember. This isn't a sign of failure, not at all. It's actually a huge, celebrated, and absolutely crucial first step on this journey. So what exactly is this noise they're all talking about? Well, it really comes down to two gigantic hurdles that everyone in the field is fighting against. The first one is called decoherence. The best way to think about this is to imagine a qubit's special quantum state is like a really fragile soap bubble. The tiniest little thing, a stray vibration, a tiny change in temperature, can make it pop. And when it pops, all that precious quantum information is gone, and it just becomes a boring old classical bit.
The second huge problem is error correction. I mean, how do you even begin to fix mistakes in your calculation when the very act of looking at the qubit to see if there's an error can cause the whole system to collapse? These are the two massive, monumental challenges that engineers are battling every single day. So just as scientists were starting to get a handle on some of these crazy hardware problems, the entire landscape shifted. The field just exploded. It went from being tucked away in university labs to becoming this high-stakes global race, with the world's biggest tech companies jumping in with both feet. And yeah, we're talking about giants like IBM and Google. They've poured billions of dollars into this, building those incredible, massive, chandelier-looking refrigerators you've probably seen pictures of. But it's not just them. They're joined by this whole ecosystem of ambitious startups and other global tech players, all competing, all pushing each other to build bigger, better, and more stable quantum computers. And they're hitting new milestones practically every year. Now, this intense race led to a ton of headlines about something called quantum supremacy. And you've probably heard this term thrown around, so it's really important we understand what it actually means. It's not about world domination, it's a very specific technical milestone. All it means is that a quantum computer successfully did one single task. It doesn't even matter if the task was useful, that no classical computer on the planet could practically complete. Think of it as the official hello world moment for this whole new era of computing. It's the proof of concept. But here's the thing. Achieving supremacy, it's kind of like climbing a small hill, only to get to the top and see the real massive mountain looming right in front of you. Proving a machine can do something unique is awesome, but it's really just step one. The real goal, the true prize everyone is chasing, is what comes next. And that goal is what we call quantum advantage. It's pretty simple, really. Supremacy is step one, just prove that the thing works. But advantage is step two, actually using that power to solve a useful, real-world problem better, faster, or more efficiently than any classical computer possibly could. That is the real finish line. That's what this entire race is about. So let's zoom out for a second and bring this all home. With this global race for quantum advantage now in full swing, what does it all actually mean for us, for the world? What is a quantum future really going to look like? Honestly, it is almost impossible to overstate the potential impact here. Remember Feynman's original idea about simulating nature? Well, because these computers literally speak the same language as the universe, they could let us do things like design brand new drugs and materials, atom by atom. They could help us create financial models that are actually predictive, supercharge the next generation of AI, and maybe even build climate models that can help us solve climate change. We're not talking about small incremental improvements here. We are talking about potential solutions to some of the biggest challenges humanity has ever faced. And of course, a revolution this big needs revolutionaries, right? We're seeing this incredible demand for a totally new kind of talent. Quantum engineers, physicists, programmers. These are the people who can actually build and code for these mind-bogglingly complex machines. It's a brand new frontier, and honestly, they are the rock stars, the pioneers who are out there exploring it for the rest of us. So what's the next big mountain to climb? Well, right on the horizon is something called fault tolerance. The big goal here is to build quantum computers that are smart enough to correct their own errors on the fly. That would finally let them run those super long, complex calculations we need. And the ultimate dream, the holy grail, a quantum internet. Imagine a network that links up quantum computers all over the world, essentially creating one single planet-sized, unbelievably powerful machine. So there you have it. From a simple, theoretical question asked by a physicist decades ago to a full-blown global race that could literally redefine our future. The origin story of quantum computing has been absolutely incredible, and it really leaves all of us with one final massive question to chew on. The dawn of the quantum age is no longer on the horizon. It's here. The only real question left is,